Hello and welcome back to our third lecture in this series on radioactivity. Today's lecture will be on Chapter 3, which is entitled Energy and the Nucleus. And the first thing I want to consider is what's considered in your book, the concept of binding energy. So we can actually look up, for instance, the mass of the particles that make up an atom. So, and these values are actually given in your book. So we know, for instance, that a proton has a mass, and we can do this in two ways. We can actually use the actual mass of the proton. That is, if we were somehow able to put this thing on a scale and weigh it, we know what it weighs. Or we can use it, we can do it in terms of what we would call atomic mass units. So we just use the unit U for an atomic mass unit. And we say that a proton has a mass of 1.007276. 1.0027. 1.007276 atomic mass units. The neutron's a little heavier. So the neutron, if we look at that, we find out that the neutron is going to be equal to 1.008665 atomic mass units. And we don't want to forget the electron, although it's quite small, but the electron also has a small value that we can give to it, and the electron is actually 0.0000548 atomic mass units. So from this, it's actually possible for us to put together, for any particular nuclide, we could actually add all the particles up that made up that particular atom, all the protons, all the neutrons, all the electrons, and we would get an atomic mass out of that. But what we actually find when we do this is that the actual measured atomic masses, the atomic masses that we actually see, are somewhat less than these values that we would get if we summed up all the particles. Well, you could ask the question, how can that be? We know that if we add masses together, we're supposed to get a mass that is equal to the sum of the masses, not a mass that's actually less than the sum of the masses. And this has to do with something, and of course that would be true if we were talking about chemical reactions. We'd expect everything to balance. But when we're talking about these kinds of reactions, nuclear reactions, we don't see that happening because there is apparently some mass that's actually lost, but it's not really lost. It's actually been converted into energy. And that energy is what we call the binding energy. So it's actually the energy that's holding the atom together. So we could actually calculate the binding energy by taking the actual atomic mass. And an example is given here, for instance, in your book. An example is given for iron 56. So for iron 56, for instance, if we do this, iron has 26 protons, and it's got 30 neutrons. And if we were to actually do this, we would find that if we took 26 and multiplied it by 1.007825, we'd get 26.203450. This is on page 42 of your book. And then if we multiply the 30 neutrons and put those in there, we'd get 30.259962. We could actually add in the electrons. There'd also be 26 electrons. They didn't bother to do that in this calculation, but that's okay. What we find is that the expected atomic mass, you could look this up on the internet and you'd find out, unfortunately your book does not give you tables of actual atomic masses, but you could look up the actual atomic mass. You could find that in a number of sources on the internet. And you find that the actual atomic mass of iron 56 is 55.934942 atomic mass units. So if we look at that, and then we actually look at the calculated mass, which in this case would have been 56.463412, we find that what we actually are losing here in the process of putting this atom together is 0.528470 atomic mass units. And that corresponds to, if we want to express this in what are known as MeVs, or million electron volts. An electron volt is actually it's actually the amount of energy that's needed to move an electron across a 1 volt electrical potential. So it's a very, very small amount of energy. But in this case, we're going to use millions of electron volts to actually represent this. And we find out that that one atomic mass unit has the equivalence of 931.5 million electron volts. So this is a conversion factor. 31.5 MeVs is 1 U, 1 atomic mass unit. So we can actually convert back and forth from electron volts to mass units by doing that. And what we find here is that the total energy, once we do that, is equal to 492. So what we're doing is we're multiplying this value times this value. So if we multiply that, 0.528470 U times 931.5 MeVs per U, the U's cancel out, and it's just 931.5 MeVs times this, and we're going to get a value of 492.3 million electron volts. It's a lot of it's a significant amount of energy because this is actually only referring to the energy of a single iron 56 atom. So if we wanted to look at that in terms of, let's say, a mole of iron 56, that would be 50 grams of iron 56, not a tremendous amount of material. We would find that we'd multiply that number by 56, we would get a really enormous number for that. And that number actually, if we compare the binding energy, we call this energy, by the way, the binding energy. So if we compare the binding energy of an atom like iron versus an atom like helium, and then we do that based on the number of nucleons, that's the number of particles that are actually present in there, what we find, interestingly enough, is that for helium, this comes out, we do the same kind of calculation. We find out that, for instance, for helium, the value is much, much lower than it is for iron. It's only 6.470 million electron volts, and there are a total of 4 particles, 4 nucleons. So the energy per nucleon turns out to be 1.618 MeVs per nucleon. And if we do the same thing for iron, since we now have 56 nucleons, well, actually we have more than that. We're only counting, I'm sorry, no, yeah, we only have 56 nucleons. So we have 56 nucleons here. It's 492.3 divided by 56, and that gives us a value of 8.791 MeVs per nucleon. So it turns out that this value is about almost 5.5 times greater than that value per nucleon. And if you actually look at this little figure 3.1 on page 43, and I don't think I'll be able to see it here. Probably not. I can't see it on my computer screen, so you're probably not able to see it. Hopefully everybody's got the book so they can actually see this in their book. I saw a flash of it, but it doesn't look like it's really illuminated well enough to be able to see it. But there is a little, for those of you that may still not have a book, let me just try to show you what this looks like. Let me erase this. it's actually plotting the relative stabilities of the naturally occurring nuclides. And kind of an interesting observation when you make this plot. It's plotting nuclear binding energy on the y-axis, binding energy per nucleon. That's what we just did for iron and also for helium. And if we plot that on the y-axis, so we've got binding energy per nucleon on the y-axis. And on the x-axis, we're going to plot a mass number. That's A. So this is the atomic mass. So we start out, and this is going from mass of 0, well, really a mass of 1 actually, all the way up to a mass of about 250. And then we divide that into 1, 2, 3, 4. This would be 50, 100, 150, 200. So we've got these various masses here. When we get up to a mass of about somewhere in the 50s, right up about here, we're going to reach a maximum. We're going to see something that's going to sort of look like this. And then this is going to start to fall off gradually. But it's going to start to fall something like that. It's more of a curve, not a straight line. But this is what I'm trying to approximate. So what we find is that actually, as we start to increase mass number, that the binding energy per nucleon goes up, and only to a point. And that point is right around iron. It's right around iron. So what we know is that iron appears to have the most stable nucleus. That is, it's its greatest binding energy in iron. And we observe this even in astronomical phenomenon, because it turns out that if we look at the cores of stars, we find out that when stars burn using thermonuclear reactions, that they burn, first hydrogen is burned to helium, and then helium, heavier and heavier elements are build up. You can only build up, a star can only build its core up to as high as iron, and beyond that it takes other kinds of reactions, other kinds of, in other words, we can't use fusion anymore to increase beyond that particular number. We have to use things like, for instance, neutron capture to actually get higher and higher isotopes. But as far as fusion goes, this sort of stabilizes out at the atomic mass of iron. And the reason for this is kind of interesting, because because what's actually happening is as you and you might expect this, as you add more particles, you're adding more nucleons in here. These things are tending, all these forces are starting to add together, and since the force of the nucleons, the attractive force of the nucleons, that is the strong force, is much, much greater than the electrostatic force, the force of repulsion that would actually tend to pull these particles apart. That overwhelms them until you get up to this mass of iron, at which point the nucleus is now starting to get big enough that you're starting to, you've got a number of neutrons in there, and it's starting to actually weaken the strong force with respect to the electrostatic force. And as you know, when we get larger and larger masses, once we get up to a mass of whatever the mass of bismuth would happen to be, and I don't remember exactly what it is, but it's probably somewhere around 200. So in this region right here, we're going to find out that there aren't even going to be any stable, beyond bismuth, there won't be any stable nuclides at all. They're all going to be radioactive, because at that point, the nucleus has gotten so large that you now have enough spacing between nucleons that the electrostatic force actually begins to overwhelm the strong force. So in that case, then you've got all of your nuclides being radioactive, so that there is a tendency for that nucleus to want to fall apart. But it stabilizes out here, as I said, at around iron. And you'll notice also in Figure 3.1, if you look at that, that there are two really, if you look at the actual plots on here, you'll find that most of these nuclides actually fall right on that graph, but there's a couple significant outliers, and one of them is helium-4, which is sort of out here somewhere, and the other one is oxygen-16, which is also off the line. And if you look at that, you could explain that by the fact that if you actually look at the number of nucleons in both of these cases, you notice that helium has 2 protons and 2 neutrons. And if you remember, I think we discussed in a previous chapter the concept of magic numbers. So we said, just as in chemistry, when we're looking at electrons, we can actually, we know that electronic shells are filled. When they're filled, they have a particular stability. So we have 2, 8, 18, 32, etc. For nuclear filling, it's a little bit different. The numbers are different, but we actually can fill nuclear shells as well. And for instance, with nuclear shells, we have numbers like 2 and 8, and not 18, but 20, and 50, I believe it's 58, I think. I don't remember all my magic numbers, but they're in the book here. And these numbers actually, as I said, actually have to do with the filled shell. So it's 2, 8, 20, I forgot 28, and then the other one is not 58, but 50, I'm sorry. So it's 28 and 50, and then beyond that, you've got 82 and 126. But 2, 8, 20, and 28. 2 and 8, and particularly if you have 2 protons and 2 neutrons, you have what is known as a doubly magic number. So you have a magic number of protons and a magic number of neutrons, and that makes that nucleus particularly stable. In the case of oxygen, it's the same deal. We've got 8 protons and 8 neutrons, and you'd expect that to also be very, very stable. Calcium-40 also would probably be off of the line a little bit, because it would have a doubly magic number of 20 and 20 protons and 20 neutrons. But so these particular elements actually don't fit quite on the scale because of the unusual stability of those elements. So we've got we understand now the concept of binding energy of the mass defect, which is actually the difference between the mass that we know that the atom actually has and what we would have expected, adding up all the individual masses of the particles. We call that the mass defect. And once we convert that mass into energy, then we actually have what is known as the binding energy. So when we took our number of 0.528470 atomic mass units, which was the mass defect for iron, and we multiplied that by 931.5 million electron volts per atomic mass unit, we got a binding energy of that nucleus of 492.3 million electron volts. And I might have misspoke and said something about adding electrons. Of course, since we're just looking at the nuclear binding energy, we're not interested in the electrons. That's the reason that the electrons are not in there. But if we're actually calculating the energy of the entire atom, we would add in the electrons as well. So if we want to look at nuclear decay, we can do that as well using these same kind of numbers. One other thing I wanted to mention, that is a conversion if you wanted to do it, if you weren't comfortable with looking at these things in terms of MeVs, million electron volts, and those of you that are taking physics right now, you might find it more informative or more interesting to actually measure these kinds of things instead of using MeVs, to use joules, and we can do that as well. And there is a problem in here, and where I actually do that with joules. Here it is. So total energy of decay, and it's an example given in your book where we're looking at the radioactive decay of radon, radon 222, and it's decaying to polonium. So it's going to polonium, which is 218. And radon is 86. It's going to lose an alpha particle, the nucleus of a helium atom. So this is going to have to be 218, and this will have to be 84 to balance the masses. Well, if we actually do all the math here, what we're going to find out is that if we look up the mass, it tells you, it says looking up the masses, and in your book and doing the math, it just throws the masses at you. You're not going to find these, unfortunately, in a table in your book. You'll find them for, so if there's specific problems in the back of the book that you want to do, you're actually going to have to look these things up somewhere on the internet. It's one of the unfortunate faults that I find in the book, that they're not actually giving you these masses in some tabular form. But we have to deal with it the way it is. So if we take radon, and we look up its mass, we'll find out it's 222.0175570 atomic mass units. And then we're going to subtract the combined masses of the polonium, which is 218.008966, and the helium, which is 4.002603. And if we multiply that by 931.5 million electron volts per atomic mass unit, we're going to wind up with a mass of, we're going to wind up with a, well, an energy equivalent of 5.578 million electron volts. So we say that that is the total energy of decay for radon. But if we wanted to put it into the form of actually looking at this in terms of, rather than looking at it in million electron volts, but let's look at it in terms of joules, we could first say we've got 5.578 million electron volts per decay, and then we can multiply that by 1.6 times 10 to the minus third joules per million electron volts. So that's the conversion factor that I wanted to introduce. 1.6 times 1.6 times 10 to the minus 13 joules per million electron volts. And if you do that, you'll come up with one particular answer, but that would just be the number of joules per decay, and that's actually a very, very small number, the number of joules per decay. And I think I did it for, I don't know if I did it for radon. I did it for helium. For helium, that number comes out to be 9.343 times 10 to the minus 12th joules per decay. I don't think I have the joules per decay for this particular, that is for radon. I guess I didn't do that calculation. I was looking at something else in here. In any event, what they've done is they've taken that number, whatever it is, and then multiplied it by Avogadro's number, which is the number of atoms that you actually have in a mole. And if you do that, then you're going to get a number that's going to be 5.4 times 10 to the 11th joules per mole. So when radon decays, when a mole of radon, which would be 222 grams of radon, all of that actually decays to polonium. The amount of energy that's given off would be 5.4 times 10 to the 11th joules per mole, which is actually an enormous amount of energy. And to put this into perspective, your book then does another little calculation where it looks at calculating how much how much water, if you wanted to melt, see, are we trying to boil water? Let me just see what we're doing here. I have to look this up. Oh, it's looking at the amount of energy that would be required to melt a certain amount of ice. Or it's saying how much ice could we actually melt from that much energy. And if you do the calculations, you're multiplying this times 1,000 joules per kilojoule, 1 mole divided by 6.30 kilojoules, 18 grams per mole, and a kilogram per 1,000 grams, and we wind up with a number of 1.5 times 10 to the 6 kilograms. So it's 1,500,000 kilograms of ice. That's a pretty big chunk of ice that you could melt just from the heat that's given off by a single mole of radon undergoing decay. And when you realize that there's a lot of things like uranium and other radionuclides that are actually in the Earth's core, this is the reason that this planet has never really cooled down to ambient temperature. It's not because the sun is beating down on it, but if you look at the core of the planet, it's still very, very hot. Things are molten. It's all these radioactive processes are giving off so much heat that it's actually it's raised the temperature of the core of the planet to thousands of degrees. So and that's been going on now for about 4.5 billion years. So it could take a very, very long period of time before the Earth's core actually cools down to the point where it would actually solidify, if that could ever happen. Anyway, so this is just to put things into perspective, to show you just how much money, how much energy is involved in these decay processes. It's a very, very significant amount of energy. We also have, on page 45, another thing that's introduced, the concept of decay diagrams. And these are very, very helpful if you see a decay diagram, because it tells you something about the energetics of the decay, and it also gives you an idea, if you understand, if you can look at the decay diagram, it will tell you what kind of decay process is taking place. So you'll notice that this actually